ParkSEIS is a MASW data processing software. MASW was first published in Geophysics in 1999, and it generates shear wave velocity profiles in 1D, 2D, and 3D formats. And it can also perform that backscattering analysis of surface waves so that you can actually detect very localized small-scale subsurface anomalies like voids and tunnels. It can also construct the common offset sections of surface waves in which you can actually quickly inspect the subsurface conditions through the arrival pattern of surface waves. And this software incorporates all the MASW-related techniques that have been developed during last about 20 years of my own research and practice career. It is a seismic surface wave method. You first collect data in the field by using a multi-channel acquisition approach, and then your collected data will go through two steps of data analysis: dispersion and inversion. And then at the end, you will come up with this kind of 1D shear wave velocity profile, which shows a shear wave velocity variation with depths. We would put this profile at this central location of the receiver array used to collect that particular field data. And then you can repeat that measurement on successive locations along the survey line, and then you will end up with a multiple number of 1D shear wave velocity profiles, which can go through special interpolation scheme to generate this kind of 2D cross-sectional image of shear wave velocity. And also 1D profiling is quite common, for example, for the wind turbine site investigation, in which we normally put the receiver array fixed at the same location during the data acquisition, but we change our source offsets like this, and we repeat this procedure on the other side of receiver array. And then at the end of data acquisition, we can come up with a multiple number of field records from both forward and reverse shots. And this illustrates actual field records, 4 forward shot records and 4 reverse shot records, and these are corresponding dispersion images processed from these field records. Although the location of the receiver array remained at the same location, we would see dispersion images look slightly different because of first, different near and far field effects. Second reason would be the possible lateral variation of subsurface conditions were different for each case. So we have to compensate for these two additional complications, and the best and the easiest way is to stack all these dispersion images together to produce this one stacked dispersion image, which shows a very nicely developed fundamental mode trend with the highest signal to noise ratio. So from this dispersion image, we generate this 1D velocity profile. The ParkSEIS tries to utilize a fundamental mode dispersion curve. It does not include higher modes inversion as an option, and this slide illustrates why. These two are arbitrary velocity profiles, which by no means are uncommon in reality. These are just normal velocity structures, and these two are corresponding dispersion images modeled by using that reflectivity approach. These thin lines are theoretical dispersion curves for fundamental mode all the way up to 20th higher mode. So there are a total 21 dispersion curves overlapped on each dispersion image. In both images, we see this fundamental mode pattern clearly imaged. But these higher mode patterns, for example, this apparent first higher mode turns out to be actually 7th higher mode. And this apparent second higher mode turns out to be 9th. And this one is actually a mixture of 11th and 12th modes. And this one, 15, 16, 17 modes mixture. And these are more complicated. Each chunk of dispersion image actually consists of multiple modes. So the point here is whenever higher modes occur, they do not occur in order, like a first, second, third, fourth, like that. But fundamental modes occur always consistently. They always take the most dominating energy, and we cannot miss it. So if that's the case, when we try to include our higher modes into our inversion approach, we have to make assumption that we know the modal identity of our observed higher modes. For example, here, these blue lines are input dispersion curves. This one is the first fundamental mode, and this one is actually second higher mode. But during the higher mode inversion, we assume that this one is the first higher mode. And then this red line is the result from that higher mode inversion. We see the results a lot erroneous, much more erroneous than this fundamental mode only inversion, which shows very close results. So this is why this ParkSEIS does not include multimode inversion as an option, and I don't think we are quite ready yet to utilize higher modes inversion to increase our accuracy yet. It first imports field data in a seg2 format, and then it internally converts into a PS format. And this format conversion is necessary because there are many unique and special data arrangements made. And then it moves on to this step number 3, which encodes a source receiver setup into the header of each data element. Normally, this information would be encoded in the original field files. If that's the case, then the ParkSEIS will detect it and display that information graphically so that a user can inspect. And if that is the correct, then you can skip this step in number 3. Otherwise, you have to go through this step very carefully. And then I will move on to this step number 4, which will generate dispersion image. One dispersion image will be generated from one field file. So if you started with multiple field files, like 10 field files, then you will end up with 10 dispersion images generated at the end of this step number 4. And then you will move on to this step 5, where you will extract one fundamental mode dispersion curve from each of dispersion image. Then those extracted dispersion curves will be passed onto the final analysis step, which is inversion. And at the end of this inversion, you will end up with shear wave velocity profile, which can be either 1D or 2D. If you started with only one dispersion curve passed onto this inversion, then it will be 1D. And if multiple dispersion curves were passed, then the final output will be 2D cross-sectional image of shear wave velocity. And there are two types of special data analysis. One is called the common offset sorting, and the other one is called the backscattering analysis. Both of these are explained in the separate user guide, backscattering analysis and common offset sections.